Hello everyone, my name is Omar David Osorio and today I will present our project titled Implementation of a Wireless Barometric Data Transmission System using LORA and ESP32. This project was developed by my team members, Gerardo Estienne Loaiza Ortiz, Cesar Augusto Carrasco Astamorir, and myself, Omar Garay. In this presentation, I will summarize three main parts of our report: the MATLAB course we completed, the installation of the software tools required for development, and the materials and electronic components used in the system. In the part 1, MATLAB course overview, this first stage of the project involved working with MATLAB. MATLAB, or Matrix Laboratory, is a widely used engineering environment for numerical computation simulations and signal processing. We installed MATLAB using the academic license provided by the university. During the installation, we selected the necessary toolboxes, including the signal processing and communication toolboxes, which are essential for analyzing and simulating transmission systems. For the course, we completed several practical exercises. We learned how to create vectors, perform mathematical operations, generate time domain and frequency domain plots, and visualize digital signals using different markers, colors, and grid configurations. These exercises helped us understand fundamental concepts such as a sampling noise, digital data representation, and baseband transmission behavior. As part of the course requirements, each members of the group completed the official MATLAB oral certification, which verified our understanding of the software and its basic tools. Although MATLAB was not directly used in the embedded implementation of our project, it the part 3, materials and electronic components, I talk about the hardware implementation of our project is based on several key components. The central device in the transmitter node is the ESP32 microcontroller, which includes Wi-Fi, Bluetooth, dual-core processing, and multiple communication protocols such as I2C, SP, and UART. To measure the environmental variables, we used the BMP180 barometric pressure and temperature sensor, which communicates through I2C and provides accurate and stable readings. For long-range communication, we implemented the LORA SX1278 module operating at the 460 MHz. This module was chirp spread spectrum modulation, which allows long distance communication with a strong resistant to noise. In our test, we achieved on a transmission distance of approximately 30 meters in open areas. On the receiver side, we used an Arduino Uno, another LoRa SX1278 module, and a Bluetooth HC5 module to send the received data to an Android mobile application. Additionally, we used antennas for the LoRa modules, jumpers wires, breadboards, and regulated power supplies to ensure a stable operation of all components. Well, with this concludes my part of the presentation. Thank you for your attention. And now I will give the floor to my at the part 2 in installation of development tools. To program and test the systems, we installed several development tools. First, we installed Python 3.11.7, which is required for running MicroPython tools on the ESP32. Next, we installed Tony ID, a lightweight code editor that allowed used to upload and run MicroPython scripts directly on the ESP32. Using Tony, we reset the memory on the board and flashes the official MicroPython firewall ESP32 generic 2025 9.11 version 1.26.1.bin. After that, we confirmed communication through the lapel console. For the receiver node, we installed the Arduino IDE. In this environment, we imported the LoRa library by Sanded Mystery, which enabled use to the program the LoRa SX1278 module connected to an Arduino Uno. Finally, for the mobile interface, we used MIT App Inverter 2 to develop a sample application that receives Bluetooth data from the HC5 module and displays the measured pressure and temperature in real time. In summary, these tools, Python, Tony, MicroPython framework, Arduino IDE, and MIT App Inverter, we're essentially for programming, testing, and integrating each part of the system.
Methodology into installation and configuration. Python, Tony, and MicroPython were installed on ESP32. The firmware was flashed, the COM port was configured, and available voices were verified. In the end, leave the ESP32 ready to pair the script. Program mode. Programming of the transmission mode. MicroPython was implemented in a code to initialize the BMP180 configuration of the LORA to take pressure and temperature readings. Send the packet every 5 seconds. The sensor showed stability and accuracy within expectations. For programming of the receiver mode, the Arduino Uno receives the LORA transmission using the LORA touch library. The program configured the frequency, bandwidth, and power. The reception was continuous and the average delay of 100,000 of 250 milliseconds was suitable for real-time monitoring. Hardware integration, ESP32 plus BMP180 plus LORA were used on a protoboard and the Arduino with its LORA on another. Connections, power supply, and signals were checked with a multimeter. The system operated without interference or errors during initial tests. The BMP180 test, the sensor was well known and delivered stable values. It did not show excessive noise or out of range verification. The ESP32 transmitted and the Arduino received the packets without losses. It was verified that the LoRa link was stable. Using an script stream. The range test worked correctly up to 30 meters without losses. This confirms its proper functioning for remote monitoring applications. Readings were taken every 10 seconds for 5 minutes. The pressure between 750 and 750 hectopascals. The temperature between 23.3.
System implementation testing resulted on shellings. In this page of the project, we connected on the first physical implementation, physical deployment, on the wireless combination system as well as the execution of function and test. Performs testing to validate whether the sync words were met on real-world conditions. The main objective was to confirm and reliability, stability, and accuracy of the barometric telemetry platform, which integrates an ESP32 microcontroller BMP 180 barometric pressure and temperature sensor, LoRa log range, radio transceiver, and SX1278 Bluetooth module structured under and the Internet of Things adaptive LoRa Internet of Things. Hardware integration and system assembly. Hardware implementation. The programs began with the hardware integration on the transmitter node. Transmitting node, the ESP32 was used and the main processing on CPU, responsible for sensor data and acquisitions and ESP32. BMP was established through E2C combination protocol, while the LoRa is SX1278 radio module operation using SPE combination protocol, serial peripheral interface. To secure electrical compatibility, essential attention was paid to logic level signs. The ESP32 operates at 3 volts. Logic level means additional circuitry was required to protect the device from potential overvoltage. As the receive node, an Arduino One microcontroller board was combined with another LoRa module to capture the transmitted data packets. The received data was the forward wireless to mobile device using an SX05 Bluetooth combination module based on UART, universal and synchronous receiving in transmitter signals. Before testing, the combination were performed continuous checks, verified silent straight with digital multimeter, and ensured stability power, delivered toward USB and regularized supply lines. testing methodology and execution testing procediments. To validate the complement load system, the following structured tests were carried out. Sensor performance validation. These tests confirmed the proper functions of the BMP barometric sensor, ensuring that the values and atmospheric pressure and finally, with appreciation and the collaboration, teams work and dedication demonstrate speed and protect members' works effort and commit, ensure the successful completion of the work. My name is Gerardo Steven Loaiza Ortiz.